Okay, welcome back everyone to the deep dive.
Hey there.
Today we're tackling something maybe a bit unexpected, a connection between abstract college math.
Yeah, like differentiation and integration,
Yeah,
calculus stuff.
right. And something super concrete,
Right.
the energy used inside a food processing plant, where they're making your food.
It sounds like a stretch, but the sources we've got actually explore this exact thing. They show how these math concepts aren't just theory.
They're real tools.
Exactly. Tools for, well, understanding and controlling how much energy these big food factories are using.
So our mission for this deep dive is pretty clear then. We want to pull out the really useful, maybe surprising insights from these sources.
And show you that calculus. It's not just problems on a page, it pops up in some really practical places.
Driving efficiency, saving costs, all that.
Definitely. I mean, picture a food plant. You've got huge ovens, right? Chillers, pumps, conveyors,
Loads of machinery.
massive amounts, and they all need power. Lots of it.
And it's not like they just use a steady amount of energy all day, is it?
Oh, not at all. That's the key. It spikes. When they fire things up, it goes up and down depending on what they're processing.
And then drops during breaks or downtime.
Exactly. So figuring out the total energy used over, say, a whole production run, or even just one day.
That's vital, right? For costs, for reporting.
Absolutely critical. But like you said, it's not just adding up a few numbers because the rate of energy use is constantly changing.
Okay, so simple addition won't cut it.
No. And that's where integration comes in. It's perfectly designed for this.
How so?
Well, instead of just guessing with an average, integration lets engineers precisely sum up every little bit of energy used.
Like kilowatt second by kilowatt second.
Yeah, exactly.
Yeah.
Over any time period they need, even when the power demand is, jumping all over the place.
Ah, okay. So if a source talks about like a pasteurization cycle where everything's fluctuating temperature, pressure, energy needed,
Hmm.
integration is how they nail down the exact cumulative energy cost of that specific batch.
That's the idea. They're basically adding up, well, technically an infinite number of tiny slices of energy use over time.
Okay, I see.
And one paper we looked at really highlighted this. It showed that using integration for specific heating processes, well, the actual energy used, was sometimes way different from what they'd estimated using just averages.
Really?
Yeah, so it led to more accurate costs, obviously, but it also helped them spot which processes were the unexpected energy hogs.
Fascinating. Okay, so integration handles the total picture, the
Oh.
cumulative sum.
Right.
But you also mentioned efficiency. It's not just about the total bill, but how that energy is being used moment by moment.
Exactly. And that's the other side of the coin. That's where differentiation comes into play.
The rate of change.
Yep. Differentiation lets them look at the instantaneous rate of energy consumption. How fast is the power draw going up or down right now?
Why is that specifically useful?
It's crucial for understanding the dynamics of different operations, how things behave in real time.
Okay, so back to the example. Instead of the total energy to start a huge freezer over an hour,
Right.
differentiation could tell you the rate of energy draw just in those first, say, 30 seconds,
Yeah.
when the motor's really straining.
Precisely. One source gave a great example. Analyzing the derivative, the rate of change of the energy curve during equipment startup helped them spot problems.
Like what?
Well, if a motor's energy draw rate was suddenly much higher than normal right at the beginning,
Uh-huh.
that could flag a potential mechanical issue, or maybe something needs calibrating. You catch it early.
Before it fails completely or just wastes a ton of energy over time.
Exactly. It's about diagnosing efficiency problems as they happen, or even before they get bad.
Okay, wow. So you've got integration adding up the total energy bill, the whole picture,
Mm-hmm.
and differentiation giving you these snapshots, these insights into the dynamics, the efficiency, moment by moment.
You got it. It's taking these fundamental calculus concepts, things you learn in class, and applying them directly to optimizing actual kilowatt hours and real operational costs in a pretty high-stakes setting.
Not just theory anymore.
Not at all. What's really insightful from the sources is seeing how these math tools become the bedrock for things like predictive maintenance, refining processes, getting energy accounting spot on.
Especially in an industry where energy costs are such a huge factor.
Absolutely. The sources really show calculus moving off the abstract page and having a tangible impact. On the bottom line, even on the environmental footprint.
It definitely changes how you might look at these math subjects, doesn't it? Seeing them work in something as basic as making food.
It really demonstrates the power of math, to
Yeah.
model and understand the physical world all around us.
Yeah, absolutely. So maybe a final thought for you listening. as you're working through differentiation, integration, these kinds of concepts.
Think about it.
Yeah, think about what other complex, maybe everyday processes or industries might be quietly relying on this very same math,
Hmm.
hidden just under the surface.
Waiting for you to spot the connection.